Good morning, good afternoon, or good evening, depending where you are. My name is Stephen Klein. I'm from Philadelphia, and I'm delighted to be with you today to discuss a faculty that's near and dear to my heart, the Technion Faculty of Aerospace Engineering. One day in the 1980s, my father and three of his friends came to my office and said, "Congratulations, you are the new president of the Philadelphia Technion chapter." Our major project was the funding of the flight control lab for my friend, Professor Shmuel Merhav. At that time, he was a pioneer in drones. This lab is still doing research today. The security and vitality of Israel, through its aerospace industries and the IDF, has been my philanthropic priority for decades. As an active pilot myself, among my closest friends are leaders of Israel Air and Space Industries and Israel Air Force. The faculty is Israel's only academic department dedicated to research and education in aerospace sciences. Since its inception in 1954, the faculty has served a strategic role, educating leaders of Israel's military, defense, and commercial aviation industries. Conceived by David Ben-Gurion at a time when Israel did not even own a modern airplane, the American Technion Society played a critical role in building the aerospace engineering faculty, which received significant support from the late Joseph Gerwin of New York, the late Helen and Norman Asher of Chicago, and Dr. Bob Shillman of San Diego, as well as donors in the Philadelphia and Baltimore communities. Among them, the Davison family, Joseph Meyerhoff, and Isaac Taylor. We are also pleased to have Aliyah and Yigal Aarons on the call, the children of the late Moshe Aarons, who served in the Israeli government as a defense and foreign minister. What is less known that his first career was one of Technion's first aeronautical professors in the 1950s and early 1960s. Thank you for joining us. At the risk of a corny metaphor, ATS has proudly been the wind beneath the wings of the aerospace engineering faculty. They give me this material to say, but that's a little over the top, but nevertheless, it's true. Not only has this faculty trained remarkable aerospace engineers, but its students and faculty helped to build the burgeoning aerospace and defense industries that have been vital for the security of Israel. Over the years, the faculty and graduates have contributed to Israel's missile guidance and defense programs, including the Iron Dome, drone technology, the National Space Program, and more. Companies such as Israel Aircraft Industries, Rafael, and Elbit Systems can all trace their origins and success to the Technion. Aerospace and related industries contribute at least $10 billion to Israel's GDP. In fact, the close relationship between academia and industry is a continuing cornerstone of President Yuri Savam's vision for the Technion. Today, we will hear from three outstanding leaders who embody the vision and spirit that the founders of the aerospace engineering faculty had at its inception, and who will be among the brilliant minds who bring Israel into the next millennium. Professor Tal Shima, Professor Daniella Raveh, and Professor Pini Gurfil. I'm thrilled to have all three of these incredibly brilliant Technion representatives with us today. Before I turn the program over to Tal, let me tell you a little about him. Professor Tal Shima is the Dean of the Technion Faculty of Aerospace Engineering and head of the Cooperative Autonomous Systems Laboratory. After earning all three of his degrees at the Technion, and in keeping with the close university-industry connection, Tal started his career as a research engineer at Rafael, and he worked at the U.S. Air Force Research Labs at the Wright-Patterson Air Force Base in Ohio, before joining the Technion in 2006. Please use the Q&A function on the webinar screen to submit your questions to any or all of our guests. We'll get to as many questions as we can at the end of the program. Now, I'm honored to welcome the Dean of the Faculty of Aerospace Engineering, Professor Tal Shima, to the program. Tal, the floor is yours.
Thank you very much, Steve, for the kind introduction, and hello for everyone from the Technion, from Haifa, from Israel. And again, thank you, Steve, also for your support of the department and actually also the Philadelphia Flight Control Lab over many, many years. So I'm very happy to present to you today our dear aerospace department. I first entered its doors 33 years ago at the age of 18. Airplanes and all things that fly are my profession these years, or for the last few decades, but actually they are my hobby. They've been my hobby since I remember myself as a child. My room was always filled with model airplanes, and I always dreamt of being a pilot in the Israeli Air Force. I didn't succeed to get into the course, so I decided to do the next best thing, to be an aerospace engineer and to understand how these incredible machines fly. Let me tell you about this our aerospace department that, as I said, I entered it quite some time ago. It was established in 1954, and since then it's the only aerospace department in Israel. We had and still have a unique role and responsibility in shaping Israel's aerospace-related activities, both in education, in research, and in industrial work. I think we have a lot to be proud of our accomplishments over the 65 years since our inception, 66 years. And just to name a few nationwide projects that we have contributed heavily to are the Iron Dome, the Aero, and many other systems. We are very highly ranked worldwide. In the latest Shanghai ranking of world universities, we are ranked number 16th in the world. If I'm not mistaken, we are the highest ranked Israeli department in any discipline. You can see here our building where we are, that is located on the Mount Carmel campus. And as I said, the department opened its gates in 1954, and this is the first building built on campus. A beautiful historic building. In this slide now you can see our current faculty. We have 25 professors and in addition 3 long-term guests. In the table they are placed based on disciplines, research disciplines, guidance, navigation, control, fluid mechanics, aerodynamics, aeroacoustics, structures and design, combustion and propulsion, and astronautics. Next to each name, you can see in brackets the planned year of retirement. As you can see, we have quite a few retirements coming up in the next few years. And this is a unique opportunity to shape the future of the department. We've already started recruiting heavily. You can see with many young faces in this slide. I'll just go over a few of our excellent recent recruits. Joe Lefkovich, let me maybe use a pointer. Joe Lefkovich, that you can see here, is a graduate of Princeton. Michael Karp, that you can see in the bottom here, is a graduate of our department and a postdoc in Stanford. And we have many other great recent recruits. 2 of our faculty received the prestigious European grant, the most prestigious grant, the ERC. Professors Benny Chikurel and Professor Gurfil, who you'll hear later. 2 of our faculty received the very prestigious Israel Security Prize, Professor Yudilevich and Professor Ben Asher. I think I'll stop here with regard to our faculty. Our mission can be divided to two: education and research. Our student body is composed of 350 undergraduate students and 150 graduate students. Roughly 40% of our undergraduate students are what we call Atuda'im, which is similar to the ROTC program in the US. They first obtain their bachelor's degree and then go and serve in the Israeli Defense Forces. We provide all of our graduates an education that we call a balanced engineer. This is an holistic approach, and we give them the knowledge needed in the most crucial disciplines of aerospace, guidance, navigation, control, structures, fluid mechanics, design, and so on. And many of our graduates lead Israel's aerospace industries. Only 2 days ago, it was announced that our graduate Boaz Levy, class of 1991, was appointed CEO of IAI, Israel Aerospace Industries, that employs 15,000 people in Israel. Over the years, Boaz held many important positions, including heading Israel's anti-ballistic aero defense system, and we are very proud of him and many others of our graduates that over the years have held leadership positions in industry and in government. As I mentioned before, our mission is divided into education and research. Let me talk now a bit about research. Okay, we perform basic and applied research supporting national defense. Our research has an industrial impact. We have quite a few international collaborations. I'll give you some examples with regard to my own research, the research performed in my own group. In my group, we are interested in guidance of vehicles, how to plan trajectories for autonomous vehicles. For example, you can see here a vehicle or an animal pursuing another animal, and we are looking for the best strategy for that, for the pursuer to catch its prey. At the same time, looking for the best strategy for the prey to evade the pursuer. We analyze such problems, for example, using game theory. So each side tries to do the best it can, given that the other side is doing the best it can. So we have made quite a few contributions in that field, and quite recently, in the last decades or so, we have turned our focus into problems involving multiple pursuers and maybe multiple targets. And I have here an example in front of you where you have an aircraft, a missile trying to chase it, and another missile. And I'll explain the role of this missile in a second. In our community, the rule of thumb is that you need 3 times as much maneuver capability as your opponent. So if this aircraft is evading, let's say 9 Gs, then this missile that is trying to catch it maneuvers 27 Gs in order to catch it. Now, if it has more than that, it will be able to catch the aircraft. The aircraft could, of course, try to employ countermeasures and such, but today's interceptor missiles are quite sophisticated, and they won't be fooled, and they will be able to catch their target. So people have been thinking about deploying defender missiles on top of these aircrafts in order to defend them from this incoming threat. But remember that the rule of thumb that I mentioned before, that you need 3 times as much maneuver capability as your opponent. So if this guy maneuvers 27 Gs, then this guy needs to have 81 Gs. If you now try to design such a system, it will be quite large, quite sophisticated, quite expensive. But what you can do, and we've been able to show that by cooperation, this aircraft and defender missile are actually a team. They operate together. By cooperating, you can reduce the requirements from this vehicle, from this interceptor to, let's say, something like 4 Gs. So how can they cooperate? The target can, for example, perform evasive maneuvers. Therefore, this vehicle will start maneuvering, and then you'll be able to identify its logic, the strategy that it is using, And now you are able to anticipate from now until the end what it will be doing. Moreover, this vehicle can lead the interceptor missile into what we call a trap. So we can lead it into the defender. So instead of the defender maneuvering 81 Gs in order to catch this interceptor missile, it hardly needs to maneuver only up to 4 Gs, since the aircraft is leading this interceptor missile into the defender. So this is just one example of how cooperation between vehicles could be very beneficial. This is research we have been doing for the last decade or so, funded by the US Air Force mainly. And hopefully in not too distant future, we'll see such systems in operation. Okay. With regard to our partners, we partner with industry, we partner with academia, we partner with government. About a third of our research is funded by the Israeli MOD, and the rest is funded by other funding agencies from Israel and from abroad. I mentioned the US Air Force, but it could be also other funding agencies. Looking into the future, we recently derived a strategic academic development plan for the department. We try to analyze what will be the important topics of interest in the aerospace world and where we have the edge and where we can make foundation contributions. You see on this slide several of these research areas, and I'll go into some of them in my next slides. So the first topic of interest to us looking into the next decade is autonomous aviation and future aircraft design. We want to concentrate on multi-agent guidance and control. If you look at current day drones, they are able to fly on them by themselves. We envision that in the future, fleets of such vehicles will be deployed, and you need to control them in a coordinated manner, in a network. You also need to plan their trajectories and control them, taking into account civilian aircraft. So air traffic management of manned aircraft and unmanned aircraft is a topic of much interest. And autonomy of such vehicles, not just fly independently, but also be able to understand the environment you are in and to react to that environment. So these are just a few of the topics that we want to research with regard to autonomous aviation and future aircraft design. Second topic is microsatellites and nanosatellites. Two problems of interest are nanosatellite swarms and constellations. The thinking is to do more with less, to use small nanosatellites, for example, in order to do the job of one large satellite. Issues to be tackled with regard to autonomy, visual navigation and perception, path planning for these vehicles, debris avoidance, and so on. Pini will discuss this in detail later. The third topic is high-speed hypersonic air vehicles. When one says hypersonic, the meaning is traveling 5 times faster than the speed of sound. Traveling at such speeds for civilian applications as well as for military ones. This presents many scientific challenges. For example, the interaction between the aerodynamics of the vehicle, the structure of the vehicle, and the heat transfer problem, the shock and boundary layer interaction, the engine. How do you design an engine for such a vehicle? In order to be efficient, you need to use what is called a scramjet engine, where you do the combustion in supersonic speed. So inside the engine, the speed doesn't decrease to subsonic speed, but it stays supersonic. And in that supersonic speed, a particle spends less than 1 millisecond inside the combustion chamber. And in that 1 millisecond or less, you need to mix it with the fuel, you need to ignite it, and you need to stabilize the flame. People characterize this as similar to lighting a candle in the middle of a hurricane storm and keeping that candle lit for quite a long time. So this is quite a challenge. Fourth topic of interest that we envision for the coming decade for us is underwater vehicles and platforms. Many of the scientific domains involved when traveling undersea are similar to the ones in aerial vehicle experiences. Guidance is similar, navigation is similar, the flow around the body is similar, and so on. In Israel, there is no academic department that covers these research domains. We believe that we can make foundational contributions in these fields as well, and there are examples here on this slide to the specific fields, the dynamics and control, and the flow. To implement our vision and to make foundation contributions in this area, we will need to first heavily recruit faculty. We're looking into how many professors are retiring in the next decade. And we see that we need to recruit 20 faculty. This is a huge number for us, about 2 faculty a year. We will need to invest in new experimental and computational labs for this new professors. We'll need to increase our student body, to diversify it, to recruit from all Israeli sectors and recruit more and more foreign students. To do this, we have to be competitive compared to other departments in Israel and abroad. And we will have to continuously update our curriculum, invest in teaching labs, and invest in excellency programs. Infrastructure-wise, we will need again to be competitive compared to other departments in Israel and around the world. We have plans for a new faculty home with facilities for students and faculty. This is you can see it over here on the top right, architectural renderings of our new home or a suggested home. Let me now try to show you some more architectural renderings of this beautiful building. Unfortunately, my screen just froze, so give me a second. Bear with me. So here is one view from inside this new suggested planned building. Here is another one, a beautiful new home for the department. This is our vision. We plan to, or we would like to renovate our historic building to provide suitable space for research and teaching and administration. And we will need to renovate our current buildings hosting our different labs. Our infrastructure has been built in the 1960s. In order to be competitive, we'll need to upgrade them. So to summarize, for the past 65 years, our department, which is again the sole aerospace department in Israel, leads Israel aerospace-related education and research. We have a clear plan on how to make foundation contributions important, not just for the state of Israel, but for the entire aerospace community worldwide. We have a clear roadmap on how to implement this plan, as well as proven capabilities on recruiting the brightest talents worldwide in order to make this happen. And we hope that you join us in our ride into the future. This concludes my talk, and I think now I'll introduce my good friend and colleague, Professor Daniella Raveh. Daniella. Okay, so Daniella received all of her degrees in the department and was a postdoctoral research fellow at the Aerospace Systems Design Laboratory at Georgia Tech before joining the Technion. Her research is centered on the interaction between aerodynamic forces and flexible structures, known as aeroelasticity. Daniella, please.
Thank you, Tal. Hello, everyone. So I'm a woman in aerospace engineering, so let's clear this question out of the way. How did I get here? So unlike Tal, I don't have a really good answer. I'm not quite sure, but I can tell you this little story. My dad was a mechanical and civil engineer, and his work was significant. He worked for the American Israeli paper mills for all of his career, 30-something years, ever since he immigrated from Hungary after the war. And my dad studied for his master's degree at the Technion civil engineering, where he designed an effluent treatment plant that cleans the wastewater of the paper mill. So his contribution to the paper mill, to the environment, to Israel's environment was immense. And work was always at home at the dinner table in his conversation with my very smart mom. And I think I wanted to become an engineer and contribute like my dad, but not exactly like him, right? I needed to do things differently, climb a higher tree. So aerospace it was. Girls didn't study aerospace. My dad wasn't an aerospace engineer. This was my way of doing things differently. And then I fell in love. But before I tell you about my research, I want to say a few words about women in aerospace engineering and in our department. So for a few years now, the Technion is holding the Tech Women event, in which we invite about 800 high school students who study math and physics to visit the Technion and have a taste of the different faculties. And this has been going on for a few years, thanks to the very generous funds donated by Mrs. Rosalind August of the ATS. We at the faculty have been doing such events since 2013 under the title Touching the Skies, with a full day event for high school students. And we have seen an increase in female student enrollment from about 20% in 2015 to a consistent 30% in the past 3 years. Oh, and I forgot to tell you this, we were 2 in my class, so there's an improvement. Personally, I make all efforts to work with more female students in my lab as student assistants, member of project groups, graduate students. And yes, at the faculty, we're now only 2 professors, female professors out of 27, but I think it all starts at the undergraduate level. And I hope that in the very near future, excuse me, the question, how did you end up in studying aerospace engineering, simply won't be interesting. So let me tell you a little bit about my research, and I'll share my screen. Okay, my research is in the field of aeroelasticity. This is the science of interaction between the aerodynamic forces and the flexible structure of the aircraft. Airplane wings are always somewhat flexible, as you can see here in these images of different aircraft types. And then these flexible structures are acted by the air force, by the wing, and aeroelastic phenomena are what happen in between. When people ask me about aeroelasticity and what I do, I say usually that I deal with phenomena that as people who fly airplanes, you really don't want to know about, because some of the aeroelastic phenomena are catastrophic. So you're familiar with the choppiness that you feel when flying in rough air. At some conditions, the aircraft vibration can become unstable and increase to failure. So most of my research, most of the years, was in computational aeroelasticity, where I developed accurate, high fidelity methods to predict aeroelastic responses. Aeroelastic responses are a concern to all platforms, to aircraft, to missiles, even to buildings and bridges. And throughout the years, I've been working with the Air Force and Rafael, the Israeli Armament Development Authority, and other companies. And let me tell you this, even the new F-35 has some aeroelastic issues, but you did not hear it from me. So the thing is that aircraft are becoming increasingly more flexible. And this is for the good and for the bad. The trend in civil aviation is to design aircraft that are more environmentally friendly, that require less fuel and emit less of the harmful gases. And this can be readily achieved with configurations that are lighter and has a more slender wing. But this combination leads to aircraft that are increasingly more flexible and thus suffer more for aeroelastic problems. So aeroelasticity research nowadays is focused on how we can measure, quantify, and control the aeroelastic behavior such that we can mitigate these instabilities and other negative aeroelastic phenomena, and even leverage wing flexibility for more efficient and green aviation. So in the past years, I shifted my research a little bit from computational to experimental side. And I believe the proof is in the pudding, right? So if I'm designing methods to improve or control aeroelastic phenomena and I don't test them in reality, then my research is not complete. And there are two other drivers that shifted my research to the experimental side. And one is the availability and the opportunity of 3D printing, and the other is new sensors. So in flight testing of flexible aircraft in aeroelastic study, we sometimes have failures, and these are catastrophic. So the flight plan is, the test plan is very expensive, and 3D printing can alleviate this. So 3D printing offers a lot of freedom in the design and at the same time allows for a cheap test vehicle. So for the past 3 years, I've been working with a group of students from our faculty on this aircraft that you see here that we call the Active Aeroelastic Aircraft Test Bed, or the A3TB, with the goal to design, build, and test a flexible UAV platform for aeroelastic research and development. And here you can see the generation 1 from last year and the newer generation of this year. It's a flying wing configuration. It's pretty large. It has a 10 feet span and it weighs about 22 pounds, has electric propulsion, and it is all 3D printed in segments. Let me show you this nice video of two of my students putting together one of the wings, and you can appreciate how easy it is to work with printed segments. They just fit in place. The wings are detachable, replaceable, and the assembly is nice and quick. And let me tell you this coming Friday, in 2 days, weather permitting, we will test the new generation, A3TB Generation 2, with the newly designed structure. And we have research plans for it for the coming year. I would like to quickly share with you this video from our maiden flight. Oops, I'm sorry. Let me run it forward for those who don't understand Hebrew, and I'll try to translate. This is go time. Everyone's ready? Vehicle is ready. This was cleared for takeoff. One of the students is reading the airspeed. Okay, you can feel the excitement in the air. So let me conclude with this. You know how in today's environment where everything is publicized in so many different media forms, we professor must be able to frame our research as novel and groundbreaking. And as for me, I hope that in my work, I'm making my contribution to the security of Israel. I've been working with the Air Force and with other companies, and also contributing to the scientific community. But I think my greatest contribution, I hope, is in raising the next generation of aerospace engineers. We have some brilliant students in our faculty, and we would like to give them the best overall mix of knowledge and training and facility and experiences, because they will be the ones doing the groundbreaking work and the service to the country and to the research community. Okay, so thank you so much for listening. And with this, I'm happy to introduce my colleague, Professor Pini Gurfil. Pini also received all 3 of his degrees from the Technion and holds the Shirley and Bert Harris Chair in the faculty. He conducted postdoctoral research in the Department of Mechanical and Aerospace Engineering at Princeton University prior to joining Technion. He's also head of the Norman and Helen Asher Space Research Institute, director of the Distributed Space Systems Lab, and the principal investigator of the Adelis Samson Satellite Project. Pini.
Thank you, Daniella, and hello, everyone. Welcome. It's a little awkward to be speaking to you through this virtual media, but I guess we have no choice. So I'll say a few words about my background. I started my bachelor's degree in the department when I was 19. And then when I graduated, I went to the Israeli Officers Academy and spent my military service 6 years in Rafael, working as a research engineer. Back then, I was doing research and development related to anti-armor missiles and surface to air missiles and so on. And in parallel to my service, I completed my PhD. Being in academia was always a dream because of the independence and creativity. So after I finished my service, I thought it would be a good idea to go outside abroad and do a postdoctoral research. And back then, my specialty was in missile guidance and control. But Professor Moshe Gelman, who was then the head of the Asher Institute and my PhD advisor, suggested that I try on something else. He said, why don't you go and do some space-related research? I had no background whatsoever. And when I approached my supervisor at Princeton University, he didn't want to admit me, obviously because I had no background. But somehow he got convinced, and the rest basically is history. It's a passion, it's a pleasure, it's a commitment to do space research, and I want to share with you some of the stuff that we have been doing at the Asher Space Research Institute. So let me share my screen. Okay, so what you can see here in the opening slide are a couple of photos of our recent development, which are the Samson satellites that I'll talk about later on. The Asher Institute, as you can see, has a lot of staff now, students, It's a very, very vibrant research institution. Let me give you some background. So I want to give you some background on Israel's space heritage. So the original idea of creating a space industry in Israel was emanating from defense needs. After the peace accords with Egypt, Israel thought it would be good to have some intelligence on what's going on in the Sinai Peninsula. So the first surveillance satellites were developed shortly after the peace accords in the 80s. But in recent years, what we witnessed is a really major effort to develop a civilian space program. Israel is one of the few nations that has its own launch capability with the Shavit launcher. And because the Shavit launchers are quite small, the main driver for Israel's space industry was to maximize the performance of the satellites per kilogram. Israel has developed, as you can see on the slide, a number of families of satellites, including communication satellites, optical satellites, and radar satellites, very high resolution imaging satellites, top-notch, really high-tech imaging capabilities and technology. But it also developed remote sensing satellites such as the Venus satellite and academic scientific satellites. One of them was the Gurfil Texas satellite, which was the first Technion satellite launched in '94. In this context, the Astra Space Research Institute, which was established in '84, was a pioneering effort to boost space R&D in academia, which is not directly related to the Israeli space industry. So it was an idea to create a research institution that can provide high risk, high gain sort of research breakthroughs. We at the Astra Institute work with numerous partners. Obviously, we collaborate with all the major Israeli industries, including the IAI, Rafael, IAI's ELTA division, which developed the radar for the Iron Dome system. We work tightly with the Israeli Space Agency, as well as international institutions and space agencies, including the French Space Agency, the German Space Agency, and of course, we also collaborate with the Israeli defense directorates in some of the research that we do. And we also work with some American entities, including the Office of Naval Research, and recently also with NASA. The purpose of the Astra Institute is not to build satellites, but rather to use satellites as platforms for testing some of the research, space-related research going on in the Institute. The first one, as I mentioned, the first satellite was launched in '98. It was the Texa-2, which was a 50-kilo satellite. It was Israel's first microsatellite. And then after a gap of many years, we launched a new program, which is called the Aeroelasticity mission. It's a triple nano satellite mission to be launched in March. It was postponed a number of times due to the COVID pandemic, but now we're hopeful that it is going to be launched in March. I'm going to talk about this project later on. We're developing now even smaller satellites, what we call 2U. U is a unit of 10 by 10 by 10 centimeters. It's a unit used to measure standard sizes of nanosatellites. In this new project called DriveSat, we are testing some of our technologies, including a new reaction wheel and a micropropulsion for satellites. We also envision a future expansion of the Samson mission, do it more efficiently with smaller satellites. We're working with the French Space Agency and the Israeli Space Agency on an observation mission called CL, which includes somewhat larger satellites to do cloud monitoring and weather forecasting, as well as to image the activity of lightnings in the upper atmosphere. And our, I would call a futuristic project is to build a segmented optics telescope. And this way we can use really high resolution mirrors, but pack them in very small volumes. So we can get high resolution images, but with a fraction of the volume and the mass. Some of the developments we've accomplished in the past year or so. So you can see here a number of technological breakthroughs. One of them is a small thruster for satellites. You can see a coin of 5 shekels here, so you don't have the perspective, but it's really small. It's gonna be the next generation of microsatellite propulsion. We have some sophisticated digital receivers for satellite operations, a new propulsion system that was built and integrated on the Samsung satellites, the CL mission that I mentioned, a GPS disciplined oscillator, which is a system that is capable of providing very accurate timing for satellites without using atomic clocks, which are really expensive and heavy. And we've also been doing some lunar landing mission simulation center development for the future Israeli missions to that are planned to be launched to the moon. Some of the labs that we have in the Institute. So one of the labs is the Distributed Space Systems Lab. This lab is aimed at developing systems of fractionated or disaggregated satellites that can be operated as a cluster in space. What you can see here is, in this video is an experiment we did for self-assembly of satellites. The idea is to create a large satellite in space by using fragments of smaller satellites. In general, clusters of nanosatellites seem to be the future of space industry. And we have a lot of activity in the world going on, building constellations and formations of satellites. This is our electric propulsion lab. Electric propulsion is a method for propelling satellites without using the classical chemical reactions, but rather accelerating plasma in an electric field. It's much more efficient in terms of mass consumption. And one of our additional labs is called the Space Optics Lab. This is essentially a lab dedicated to development of future space cameras and telescopes. The idea here is to create what we call a virtual aperture. So instead of having a regular mirror that collects the light and provides the images, we're using a folding mirror. This mirror can open up in space and provide quality images. But as you can see, it occupies really a small fraction of the volume of the launcher. So we can really use very high diameter mirrors, meaning that you can get better resolution images. Our newest lab at the Institute is called the Aerospace Plasma Lab. What you see here in the movie is a miniature electric propulsion system for satellites. The scale here is about 5 millimeters. It provides a minuscule amount of thrust, but it's sufficient to hold a small satellite in space without the decay induced by the atmosphere. This is a short clip showing the Mission Control Center that was established a couple of years ago in the Institute as part of the Samson project that I'll describe shortly. Samson is a triple CubeSat mission, small satellites. Each one is the size of a shoebox, with the purpose of doing geolocation. Geolocation is the process of calculating the position of some emitter on the ground based on signals coming from this emitter. We established this ground station in collaboration with the Israeli company called Orbit. It's a leading company in satellite communication. As you can see, it was quite an operation. These antennae are capable of working in various bandwidths, and we need a sophisticated machine actually to track the Samsung satellites. Due to the fact that we have 3 satellites flying in formation, we need this antenna to work very fast, so we can steer it very fast to track the satellites. And this radome that you can see is just to protect it from wind and other atmospheric perturbations. So this one is already operational and it's ready to track the Samsung satellites. So I already talked about the Samsung mission. It's a really innovative mission. It was done with collaboration with the Israeli industries, IARFL and ELTA. The purpose is to show that we can actually launch the formation of 3 satellites that can work autonomously in space without intervention from the ground. And also that we can track and locate an electromagnetic radiation coming from the ground. This machine is really a sophisticated little creature. It has, although it's the size of a shoebox, it's packed with high-end avionics. Most of it was developed by the Astra Institute in collaboration with the Israeli industries. It has multiple
Sorry about the technical difficulty, but I do want to thank all of our participants for their fascinating insights. Not only is the aerospace faculty undertaking extraordinary research, but as we've heard, playing a critical role in Israel's economic, security, and technological endeavors. Now I'd like to introduce Alyssa Gilliston, ATS Director of Development in Philadelphia, who's doing a terrific job in developing the Technion presence in our community. She will moderate the question and answer portion of our webinar. Again, please use the Q&A function to submit any questions you may have.
Okay, hello everyone. Thank you so much, Steve. Of course, it's a pleasure working with you here in our fair city of Philadelphia. And thank you, of course, to all of our panelists. We do have some questions coming in. We have just a few minutes to address them, so keep them coming and we'll try to get to all of them. My first question is actually applicable to all of our panelists because you are all lifers. You've spent your academic careers starting from your undergraduate studies at the Technion. How has the department changed since you walked in the door your very first day as a student? What's changed, what stayed the same, and where is it headed?
The face has changed. Many things changed, stay the same. The faces of the professors changed. The students stay young. Always they stay the same age. So this is quite unique. I think the focus of the research changed. I think in the past it was more oriented to to basic physical understanding of aerodynamics, hydrodynamics, and such. And I think nowadays it's more oriented towards maybe algorithms, strategies, and such. This is at least in my field. Maybe Pini, Daniella can complement my answer.
I think the spirit has changed. There's more energy now because I think now we're a younger faculty. We have a lot of faculty members that are not Israeli natives, basically coming from abroad. This is a major change. So I think that we've become globalized. We're much more aware of international collaboration, much more open. I think we're less localized in our activities. We try to anchor the activities in the global context of international research, but at the same time, we're still very committed to what's going on in the Israeli defense industry. So I think basically the major change is the internationalization of both the faculty and the research.
Thank you. I think we have time for just one more question. Also, everyone is welcome to chime in. From the perspective of your faculty with regard to Israel's strategic and defense challenges, what keeps you up at night? What worries you? And how can the faculty address those security needs in future years?
What really keeps me awake at night, and I assume the same is true also for Pini, is that both our sons serve in combat units. And my son is stationed in the Golan Heights and on the border with Syria. I don't know where Pini's son is now stationed. This is really what keeps us up at night, I think. Academically speaking, my concern is ballistic missiles, many of them shot at us one night in the future, and how we can protect ourselves against them in an efficient manner, and to devise methods to do that. I remember in the 2006 Lebanon war, the second war, we had missiles coming at us. My family was sent back to the south of Israel, and it was a great time to finalize some idea I had about a new concept for intercepting ballistic missiles, and hopefully someone is using it. So this is what I can say about that.
Okay, I think we unfortunately are running low on time. So I want to, of course, thank all of you for the fantastic conversation. And Tal, I believe you'd like to offer a few closing comments.
I would just like to say thank you everyone for joining us and hearing about what we have done and what our plans for the future are, and looking forward to collaborate and interact with you in the future. And again, Steve, thank you for your continued support.
Thank you, Tal, and your staff for joining us.